Hello everyone. So in today's lecture we will start a new topic which is on intermolecular interactions. We will be talking about molecular interactions or interactions between molecules. So this is intermolecular interactions. Now what do we mean by intermolecular interactions and why it is important to understand them or to study them? You remember that matter exists in three different forms like gaseous form, liquid form and solid form, where liquid and solid are known as condensed phases of matter. Now the existence of condensed phase, if you remember the very beginning discussion at the very beginning on real gases, what are the experiments of real gas, that the existence of liquid phase actually tells that there is an attractive interactions or overall there are interactions of various types between the molecules, and that basically leads to a cohesive force which actually depends of course on temperature, and then you can have a very particular state of matter going from gas to liquid and liquid to solid. Now in this chapter we will be discussing on this nature of these forces or nature of the potential on the molecules which basically acts between the molecules. Now of course you also probably studied quantum mechanics, where we talk about the very structure of molecules, why molecules are formed and how are the forces acting between the constituents between of the molecules, like what are the forces acting between two atoms. And there probably you have studied the electronic structure of diatomic molecules in detail, where you studied that formation of a chemical bond is very much quantum mechanical in nature, because when you bring two hydrogen atoms together and form an H2 or H2 plus, which is a more simpler system, one electron system. So there you studied that there are two kinds of forces. One is Coulombic force, which is every force is electrostatic. But the electrostatic force is one is Coulombic force, which is basically the attractive force between the electron and the two nuclei, and also the repulsion between the two nuclei. And but that force does not stabilize the molecule which is H2 plus. There are also other forces. So the other force is basically known as exchange force. And the exchange force is basically, you can visualize that the electron is basically shuttling between the two atoms, and although it is not a very rigorous way of saying that it is shuttling between the two atoms, because it is very much quantum mechanical in nature and you cannot visualize it very properly, but the existence of chemical bond is due to the exchange force. Now moving on, one can now think about what happens between the molecules. In a similar way, you can actually think about the interactions between different H2 molecules, or say different H2O molecule. That will be a more specific molecule to discuss, and thereby you can actually understand what are the specific interactions between the water molecules that give rise to the condensation of H2O molecules, which actually leads to formation of liquid water from water vapor. Now those kind of forces we will be understanding or trying to understand in this lecture. Now let us begin our discussion. What are basically these forces? Now all of you know that most of these forces are, which are intermolecular forces, are of Coulombic in nature, in the sense that there will be some electron cloud around each atom, or overall in the molecule there will be some electron distribution, and due to this electron distribution there will be some dipole created in the molecule, and that dipole basically attracts with another molecular dipole, and thereby there will be an attraction between the water molecules. But what we are talking right now is basically about permanent dipole moments. Now a molecule may not actually possess a permanent dipole moment. For example, helium atoms, they do not possess any permanent dipole moment, because helium it is basically monatomic. Let us say nitrogen molecules, these are also do not have a permanent dipole moment, or any homonuclear diatomic molecule, they do not have permanent dipole moment. So there we have actually induced dipole moment, and then we have interactions between the different induced dipole moment, which can lead to some attractive interaction overall. So we will be talking about that. So let us first define what is a dipole, and already you know in from your high school physics that what is the definition of a dipole. So if you have a charge distribution where I have say a charge which is of magnitude plus q and another charge which has a magnitude of minus q, and suppose these are the locations of the two charges, and suppose they are separated by a distance r. So then the dipole moment is defined as or the magnitude of the dipole moment is defined as q times r. I am using small r, so maybe we can write it, replace it as capital R. So this is the magnitude of the dipole moment. Now dipole moment is a vector quantity, which means it has x, y and z components, and actually if we want to write or want to know the direction of the dipole moment, the convention is basically it is acting from the negative end of the dipole to the positive end of the dipole. Now the older convention was basically going from positive end to the negative end and writing a plus sign here just to indicate that this is the positive end, but we will stick to the new convention. Now dipole moment also has some unit, and as you can see the unit will be like unit of charge times unit of displacement. So you can think that the SI unit of charge is coulomb and the distance is meter. So the natural unit is coulomb meter, but there is a useful unit which is basically have been used to measure the dipole moment of molecules and atoms. Atoms do not have permanent dipole moment, molecules and ions and many other species. So that unit is known as dBi unit, which we write as d, and this is the after the name of Peter dBi, who did a lot of pioneering work on measurement and formulation of molecular dipole moments. And there is a relationship between dBi and by definition. So this coulomb meter definition will be something like, if I have one coulomb positive charge and one coulomb negative charge which is separated by 1 meter, then the dipole moment will be 1 coulomb meter. Similarly, we can define a dBi, which actually tells us that if I have two charges which are one electrostatic unit, these are the CGS unit of electrostatic charges which you have studied probably in high school physics, and if they are separated by 1 centimeter, so then this 1 ESU centimeter is equivalent to 1 dBi. So there is a relationship between 1 ESU centimeter and coulomb meter, and usually we write that 1 dBi is 3.33564 into 10 to the power minus 30 coulomb meter. Now, as I said earlier that this unit dBi is very useful for polarizabilities of the molecular dipole moments. We will come to polarizability later. We are now talking about just permanent electric dipole moment. So then we can say that this the reason behind this choice of dBi is that usually at molecular dipole moment are on the order of few dBis. For example, I have I can write some of the examples here. For example, HCl, which is a permanent electric dipole moment, hydrogen chloride molecule that has mu equal to 1.08 dBi, and for Hi, hydrogen iodide, it is 0.42 dBi. So as you see that the molecular dipole moments are on the order of dBi, so it is still a very useful way. And the first example which we started with, H2O, has a dipole moment of 1.85 dBi. Now the question is, how do you know that a molecule possesses a permanent dipole moment or not? That is very much connected to the symmetry of the molecule, which is actually more fundamental property, which we are not going to discuss here. So you probably studied the symmetry of molecules in quantum mechanics course or any other specialized course on the symmetry of molecules. Now, for example, as we just said, in water molecule, so the oxygen atom will be always will possess a partially negative charge, which is due to the fact that the hydrogen is less electronegative than the oxygen. So you can actually write it as delta plus and delta minus way. So because there is a bond moment of the OH, and similarly for the other bond will also have a moment, and so we can actually write that the partial negative charge on the oxygen atom will be 2 delta minus, something like that. And due to this, there is a charge separation, and you can now think due to this bond I will have a dipole moment which actually acts in this direction, and due to the other bond I will also have another dipole moment which actually acts in this direction. And since dipole moment is a vectorial quantity, they do not actually cancel out. We will have a net dipole moment which acts as in this direction. However, you can think that if I have a linear molecule, something like carbon dioxide. So for carbon dioxide, which is a linear molecule, there also you have the partial negative charge on oxygen and partial positive charge on the carbon atoms. But here the interesting thing is, so there is a dipole moment due to this CO bond, and there is also a dipole moment for this CO bond. And because of the geometry, these two and the orientation of these two dipole moments, or two bond moments to be more specifically, the net dipole moment is 0. But for water, since it is a bent structure, the net dipole moment is non-zero. So dipole moment actually depends, so the existence of dipole moment depends very much on the symmetry of the molecule. But again, we are not going to go into the details of the symmetry properties of the molecule. So let us now focus more on the dipole moment. If we have say addition of many dipoles like we have done here, what will be the resultant dipole? And since it is vector, so the general addition, subtraction rule of vectors are also applied here. So for example, if I have two dipoles inside a molecule, which are permanent dipoles, which are you can think as bond moments. So then the resultant dipole moment will be nothing but if this is suppose mu1 and this I call it as mu2, and then the resultant dipole moment will be mu1 square, or the magnitude of the resultant dipole moment will be mu2 square plus 2 mu1 mu2 cosine theta, where theta is the angle between the two dipole moments, and we are talking about only the magnitude. So for example, if I have two mu's similar, so let us say if mu1 is equal to mu2, something like we have seen for water, where these OH bond moments should be equal, because it's just identical atoms O and H. So if that is the case, so we'll have for water the resultant dipole moment for water. Now you notice here carefully, so I will just adjust the mu's same. So it will be let us say mu1 equal to mu2 equal to mu. So these first two terms will be twice mu square, and the second term will also be twice mu square. So I will have totally I can take twice mu square as common, and then I will have 1 plus cos theta and square root of that. So and then we can actually apply the cosine rule, like cosine 2 theta is nothing but 1 minus 2 cos square theta. So we can write it is as 1 plus cos 2 theta is basically 2 cos square theta, or here actually I can write the theta as 2 times theta by 2. So I am writing it as 1 plus cos theta is nothing but 2 times cosine square theta by 2. So ultimately I will have 4 mu square cosine square theta by 2 square root of that. So ultimately the resultant dipole moment comes as twice mu cosine theta by 2. So that will be for that's a general principle. Now we have to find out the angle for water molecule, what are the angle, I mean if it is water molecule we can actually just calculate it very easily, but this is the expression which we just derived. This is for any general molecule where actually we have two dipoles which are of equal in nature, and there is an angle between them which is theta. Since we can actually add the dipole moments, the interesting thing is that suppose for benzene we have all hydrogen atoms here, as you already know, and as you can think that all the bond moments will basically cancel with the opposite bond moments, like this CH bond moment will be cancelled by this CH bond moment and so on. So, if we actually have a substituted benzene, something like let us say a chlorobenzene like this, so we can actually readily predict that there is a CCl bond moment and there is a CH bond moment, and they do not of course cancel with each other. So, we will have some resultant dipole moment for chlorobenzene. But similarly, if we have say dichlorobenzene, like say ortho substituted dichlorobenzene, something like that. So, you can think that it will be as if the dipole moment of two chlorobenzene molecules. So, for chlorobenzene the dipole moment direction will be like this, because chlorine is more electronegative and our choice is from negative to the positive end, and for chlorobenzene we can actually get the resultant dipole moment along this direction. So, how do you find it? So, this is also very easy to understand, because the as you can see the angle between them will be nothing but 60 degree. So, this angle will be right 2 mu cosine 60 degree by 2 or 2 mu cos 30 degree. So, we can actually get a ratio of the dipole moment between two disubstituted benzene. For example, if we ask this question, what will be the resultant dipole moment for the ortho disubstituted chlorobenzene, and what will be the resultant dipole moment for the meta disubstituted chlorobenzene. And remember that for ortho actually the angle is 60 degree, but for meta, as you can very easily figure out, that this angle will be 120 degree. And here the bond moments or the individual dipole moments are basically same, because it is just chlorobenzene. So, it is a CCl, and opposite to it in the trans position, not transposition, in the just opposite carbon position. So, you have the and opposite to it in the para position you have a CH dipole moment. So, the resultant will be same, and you can think that as if for these disubstituted benzenes it is basically a resultant of the two dipole moments, but oriented in a particular angle. So, for ortho this angle will be this ratio will be nothing but cosine theta by 2 for ortho divided by cosine theta by 2, where this theta is for meta. So, what we will have is it is the top one for ortho, actually it is 60 degree, and 60 divided by 2 is 30 degree. So, cosine 30 degree is root 3 by 2 divided by, I will have cosine 120 degree by 2, which is cosine 60 degree, which is 1 by 2. So, overall we will have the ratio as root 3, which is nothing but 1.7, and this again follows from the vectorial addition of dipole moments, because the dipole moments are basically vectorial in nature. Now, the next thing is that here we have given you a very nice example, in the sense that I have two bonds and there are some bond moments which are individually dipole moments, and these two dipole moments are permanent dipole moments which are oriented in space in a very particular angle, and due to this angle which is dependent again on the molecular geometry, so we will have basically a vectorial addition of the dipole moments, and we can get the resultant dipole, and for that actually you can calculate the dipole moment of the disubstituted benzene from the monosubstituted one, or you can actually calculate the ratio of the disubstituted benzenes in the way we have shown here. Now, here look at it carefully, that this resultant dipole moment is higher for ortho than the meta, which makes sense, because if your angle is small, suppose this if the angle would have been 0, So then the cosine 0 will be 1. So the resultant dipole will be just twice mu. And if the angle is 60 degree, it will be something like that. If it is 120 degree, it will be something less than that. And if it is 180 degree, then the dipoles will cancel with each other, something like we have seen for carbon dioxide. And then they will have a perfect cancellation of the dipole moments, and the resultant dipole moment will be 0. So it all depends on the angle between them, but for a polyatomic molecule where actually we do not have such a clear separation of very nice dipole moments and from a particular origin, then we can actually still work out and find a dipole moment from a particular point in space or the origin. So in that case, what we do is that you basically calculate the partial charge or electron densities more specifically in on each atom, and then you basically do a vectorial sum. So to be more specific mathematically, so what I am saying here is that the resultant mu, suppose I have a total mu like this, and then what I am writing is that suppose I have many atoms in this, suppose this is an arbitrary molecule, and these are basically atoms, and each atom has some electron density around it, and for that we have some charge, and then we can actually ask this question, what is the x component of the dipole moment? And then what we have to do is that we have to find the position of each atom. Suppose each atom I am writing the ith atom as xi, and then we can actually associate the partial charge for this ith atom, and this position is with respect to some origin. Let us say this is the origin, and then we will find that, for example, for this atom, what is the coordinate along say x axis, if this is our x coordinate, and what is the coordinate along say y axis. So suppose this was the y coordinate, and then we can actually write down the x component dipole moments as the sum of all the x component dipole moments for individual atoms, and then we sum over all the i's. Similarly, for y direction also we can get a similar way. So the charges, partial charges, times basically the position of that atom. So since we are talking about now the y component, it will be something like yi, and similarly we can also talk about the z component of the dipole moment, and then we can get something like this for individual atoms, and then we can actually talk about the total overall dipole moment, which will be nothing but mu x. And if we want to have the addition of vectors, so we have to also multiply by the unit vector mu y into j plus mu z into k, where I, j, k are basically the unit vectors along x, y and z direction, or we can get the direction or magnitude of the overall dipole moment as square root of mu x square plus mu y square plus mu z square. So we will give you an example where we will actually tell you a particular bond, which is the amide bond, and we will be talking about the amide bond is very important in peptide chemistry, because when two amino acids basically form a peptide bond, it is basically the amide bond which we talk about, and more or less the geometry of the amide bond is planar. So the amide bond is something like this, and you can now think about the partial charges on hydrogen, on nitrogen, on carbon and oxygen. And why the amide bond is planar? The reason is because of this lone pair on the nitrogen, this amide bond, the NC bond, actually has a partial double bond character. So this is known as a resonance structure, which probably you already know. So this NCO unit actually basically relies on a plane, so that gives the planarity of the amide bond. So these are basically resonance structures, and this is basically a resonance hybrid structure of the amide moiety. You can actually calculate, if you know the partial charges along a particular and the position of each atom from a particular origin, then you can actually calculate the overall dipole moment of the amide bond. And in this way, you can actually find out what is the overall dipole moment of a particular group in a molecule. You can also find out the overall dipole moment of the molecule itself. Now, the question is, dipole moment is not the only thing that the molecule poses, because here we are talking about the distribution of charges in the molecule, and we talked about only dipole. Now, dipole is not the only thing that we have, and we also have something like quadrupole. What is a quadrupole? We already gave you an example, which is carbon dioxide. Now, this is basically higher order moments, and this comes from detailed tensor algebra, which we will not consider here. So, for example, CO2, which does not have a permanent dipole moment, can actually have a quadrupolar moment, and let me actually show you the negative as in a different color and the positive also in a different color. But for a dipole, for a similar drawing, we have already shown how the dipole is represented. So, dipole is represented as the separation of the two charges like this, and similarly you can also think about a monopole, which is either a positive charge or a negative charge, something like this. So, we have actually many different poles, or these are actually in general called multipoles. So, like monopole, then we have dipole, and then we have quadrupole. You can also get quadrupole from a very different arrangements, but we are not going to the details. You can actually find it in the recommended text, which you are supposed to have a look at. And then also you have octupole and many other distribution of the charges, but those are very particular distribution, in the sense that the way we have described it, like we can have a dipole, like it's basically two distinct distribution of two distinct charges. Then we have quadrupole, which has a very particular arrangement, like it's a linear arrangement of a negative charge, then twice the positive charge, which has basically a charge of twice the negative charge, then again another negative charge, something like that. Now, in reality, a molecule will have a moment which is not like this, because you will have an arbitrary charge distribution, but you can always write this arbitrary charge distribution at the total moment due to this arbitrary charge distribution as a linear combination of monopole plus dipole plus quadrupole plus octupole and so on. So, basically these are geometrically having basically symmetric moment structures, and any multipolar moment, or basically what you call as any moment of a multipole can be thought of as a superposition of monopoles, of many multipoles basically. So, what I am saying, the moment of any arbitrary charge distribution, moment of any arbitrary charge distribution, that can be thought of as a superposition of many multipoles, and the multipoles are basically monopole, then we have dipole, then we have quadrupole, then we have octupole, and so on. So, again this in this discussion you always remember that when you go for an higher order higher order multipole, for example, if you are going from the monopole to the dipole, then the monopole actually contains a net unit charge. The dipole does not have a net unit charge, but it has a dipole moment. Then the quadrupole does not have a net unit charge, because as you can see it is a minus delta minus 2 delta plus delta minus. So, there is no net unit charge, and also there is no dipole moment, but it has a quadrupolar moment. And then similarly for an octupole, if we talk about, it does not have any permanent charge. So, it is not a it does not have any monopole, it does not have any dipole moment, it does not have any octupolar quadrupolar moment, but what it has is basically an octupolar moment. So, these are all basically fundamental charge distribution, and with that we can actually constitute the higher order moments, and any arbitrary charge distribution we can actually write in terms of that. But we will not extend our discussion on this multipolar moments right now. Rather, we will be now focusing more on the dipole moment, and what happens for basically if we actually have an external electric field if it is applied to a molecule. So, let us try to understand that first. Now, the way we have talked about it is basically I have a permanent electric dipole moment. Now, this permanent electric dipole moment, sometimes the molecule may not have actually a permanent electric dipole moment. However, due to the presence of an electric field, the dipole moment can be created. Now, how one can visualize this phenomenon? Now, as you know that the simplest charge distribution or the simplest entity or simplest atom we can think of is the hydrogen atom. And in the hydrogen atom, what you can think that there is a positive charge. We are actually writing the positive charge as green center, something like this, and there is a diffused electron cloud around it, but which is basically electron cloud, but the center of the electron cloud actually perfectly coincides with the center of the positive charge. So, as such there is no separation between these charge centers. So, which means that the R in the dipole moment expression, or the distance between the positive and the negative charges, is 0, for which the permanent dipole moment of any atom is basically 0. Now, there can be instantaneously electron cloud fluctuation, which can actually give to partial separation over a very short period of time of this electron center of the electron charge distribution and the nuclei, and that can actually give rise to a momentarily dipole, but that we are not considering at this moment, and this dipole is basically arises out of own, because it is just a time dependent dipole. But if you think that on average this electron cloud will basically orient itself in many possible directions, so the orientation of this dipole will be very random. So, on average you can think that the average position of the negative cloud with respect to the positive cloud is basically they are already they are always superimposed on the time average position. So, there will be no permanent electric dipole. Now, suppose we are applying an external electric field along, say, this direction, and the electric field, as you know, basically will push the electrons and the nuclei in the opposite direction. And as a matter of fact, what you will see is I will have positive end here, and the center of the electric charge will be slightly shifted, something like that. Now, this you can realize, suppose if I put the hydrogen atom inside a capacitor, where this is basically the negative end of the capacitor and this is the positive end of the capacitor. So, the capacitor will try to distort the electron cloud, it will try to pull the electron cloud and also pull the nuclei, and then I will get a small separation and I will create a dipole. Now, this dipole is a static dipole at this moment, because we are just applying a static electric field, which you can visualize as applying or placing the molecule or the atom, in this case it is a hydrogen atom, inside a capacitor. Now, that dipole is not a permanent dipole, that dipole is an induced dipole moment, because it appeared due to the presence of the external electric field. Now, there are two things here. Atoms and molecules, since they actually have electrons and nuclei, whenever we apply say for example an electric field, we are usually considering the electric dipole moment here, but similarly we can also talk about the magnetic dipole moment, where actually we apply an external magnetic field to it, but we are not talking about magnetic dipole moment right now. We will be only focusing on the electric dipole moment at this moment. Now, if we create an electric dipole moment like this, and that dipole moment we write it as mu suffix IND. So, IND means actually this is induced dipole moment as opposed to the permanent dipole moment which we have just discussed. So, then you can think that the strength of this induced dipole moment to some approximation will be proportional to the strength of the applied electric field, meaning if the electric field is too strong, I will actually distort the electron cloud and move the nuclei in the other direction more and more efficiently. So, I am basically increasing the distance between them, which means the magnitude of the dipole which is created or which is induced will be more and more. Which means actually the strength of the magnitude of the induced dipole moment is proportional to the electric field, or we can actually write the proportionality constant as something like alpha. Now, this alpha is known as the polarizability. Polarizability of the molecule, or we will come back to the other higher order. Let us just it can be actually proportional to the nonlinear way on the electric field also, but let us not discuss it at this moment. Let us now focus on the polarizability or the alpha term. Now, what is alpha? Now, you can think that mu is a vector quantity, as we already know. So, mu will have basically mu x, mu y and mu z, and suppose this direction is let us say it is x direction. So, I have an x component of the dipole moment, and then I also apply the electric field along x direction. So, in this case this alpha is nothing but scalar, because you have only one vector which is mu x, and if the other two components are 0, which means actually the mu is only along x direction. We can write it something like this, like we have x component, y component and z component as 0, and as you know that we are writing it as a column vector. So, basically this alpha in that case is just a number, because the electric field is also applied along x axis. However, this may not be so simple like this, because you can still apply an electric field along x direction, but you can create a dipole in the x and y direction also. Meaning, what I am trying to say here, I can actually apply an electric field in Ex, but then I can actually create a dipole which has components along mu x, mu y and mu z, all these components. And in this case, as you can see that this is basically one row, one column kind of matrix, and so that is why the alpha is just a number. But if we have components like this 3 by 1, and then this alpha is nothing but it has to be 3 by 3 matrix, because you can have in more general that the applied electric field along x can actually induce the dipole moment along x, y, z all the direction. In this case, alpha is basically in this case matrix. I mean it's basically 3 by 3 matrix, and in more general alpha is basically or the hyperpolarizability. So, we will come back to what is hyperpolarizability. Alpha in this case is a matrix, but we will not go into the details. We will just consider alpha here as a number, in the sense that or a scalar, so that if we are assuming that if we apply the electric field along x, we will always have a dipole moment along created along x. So, you can think that from matrix multiplication that I will have terms like alpha xx, alpha xy, alpha xz, something like that. So, if I want to know what are the magnitude of mu x, so mu x, as you can see, will be alpha xx times Ex, alpha xx times Ex plus alpha xy times Ey plus alpha xz times Ez. So, what I am trying to say here, when we applied the electric field along Ex, we created a dipole moment along mu x, we also created a dipole moment along mu y, something like that, and also it has a dipole moment along Ez. Or we can actually view, or we can ask the different question, what is mu x, and mu x is actually contributed by both Ex and Ey as well as Ez if it is a 3-dimensional problem, and thus we see that applied field along a particular direction may create actually a dipole in all other direction. Now, you can actually think about a crystal where actually the electrons have a very unique distribution, and if the crystal axis does not match with the applied electric field axis, then actually you can create a dipole in all other direction. But you can think that I can always rotate the crystal in such a way that I'll get rid of this, meaning I'll always if I apply the electric field along Ex, I'll always get the component along Ex, and so on. If I apply it along Ey, I'll get always along Ey. So mathematically you can say that in that case we are basically diagonalizing this matrix, meaning all other components of this matrix is 0.